Welcome to The Explainer. Today, we're embarking on a massive, centuries-long detective story to decode the ultimate invisible force, gravity. I'm absolutely thrilled to guide you through this, because we're going to trace how humanity went from literally just watching objects hit the dirt to calculating the precise math needed to escape our planet entirely. It all kicks off with a totally relatable question, one you've probably thought about yourself at some point. If everything heavy falls straight down when we drop it, why doesn't the moon just crash into the Earth, right? And why do the stars seem to just float up there in the sky? To answer that, here is our roadmap for today. We'll be looking at decoding the cosmos, Kepler's 3 laws, the universal law of gravitation, weighing the Earth, gravity at different altitudes and depths, and finally, achieving escape speed. Starting with Section 1, Decoding the Cosmos, a Starry History. Let's dive right in by looking up at the night sky, exactly like our ancient ancestors did. You know, for thousands of years, humanity really struggled to make sense of the wandering planets. About 2 millennia ago, Ptolemy proposed a geocentric model where literally everything revolved around the Earth. But to make his math work out, he had to invent these wildly complicated schemes. I'm talking circles moving inside of larger circles. It was a mess. It actually wasn't until the 5th century that the Indian astronomer Aryabhata mentioned a heliocentric, or sun-centered model. Fast forward 1,000 years, and Nicholas Copernicus made the definitive case for it, even though it got him into some pretty deep water with the church. Finally, in the 17th century, Galileo stepped up. He ran actual physical experiments, rolling bodies down inclined planes to prove that absolutely all objects, regardless of their mass, accelerate towards the Earth at the exact same rate. Game changer. Moving to Section 2, Kepler's 3 laws, the geometry of space. While Galileo was busy dropping things on Earth, another brilliant mind was looking at how things moved up in the heavens. Johannes Kepler took decades of incredibly precise, naked-eye stargazing data from his mentor, and he actually cracked the underlying geometry of planetary orbits. And what's really fascinating here is just how beautifully simple Kepler's realization was. Imagine taking 2 pins, sticking them into a board, and pulling a string taut with a pencil to draw a shape. You don't get a circle, you get an oval, an ellipse. Kepler realized planets don't move in perfect circles like Copernicus thought. They move in ellipses, with the sun sitting slightly off-center at one of those pinpoints, known as a focus. He also had a second stroke of genius. He realized that as a planet orbits, an imaginary line drawn between it and the sun sweeps out perfectly equal areas of space in perfectly equal amounts of time. These observations basically became the foundation of Kepler's 3 laws. The law of orbits gives us that elliptical shape. The law of areas mathematically proves that planets actually speed up as they get closer to the sun and slow down when they get farther away, all driven by the conservation of angular momentum. And finally, the law of periods gave us a strict mathematical relationship between a planet's distance from the sun and the length of its year. So Kepler gave us the how. Which brings us to Section 3. The universal law of gravitation, the invisible force. Kepler gave us the shapes of the orbits, for sure, but it was Isaac Newton who finally gave us the why. We all know the legend of the falling apple, but what Newton actually realized from it was profoundly unifying. The exact same invisible force pulling that apple to the grass is the exact same force reaching way out into space to keep the moon tethered in its orbit. It's truly a universal connection. He calculated that this force depends on just 2 things, how massive the objects are and how far apart they are. But here's the kicker. If you double the distance between 2 objects, the gravitational force doesn't just cut in half. It drops by a factor of 4. It's an inverse square law. So here is an absolutely crucial point, and it's something that trips people up all the time. The difference between the 2 G's in physics. We never want to confuse big G with little g. Big G is the universal gravitational constant. It's a baseline of gravity for the entire universe, whether you're standing on Earth, exploring Mars, or floating in the Andromeda galaxy. Little g, on the other hand, is just the local acceleration we feel specifically here on the surface of the Earth, which, as Galileo calculated, is about 9.8 meters per second squared. Let's jump to Section 4, weighing the Earth, the ultimate lab experiment. Newton's equations were breathtaking, but there was a pretty big catch. To make the math actually work to calculate the mass of planets, scientists needed to find the exact numerical value of that universal big G. They somehow needed to bring the cosmos right into the laboratory. Enter an English scientist named Henry Cavendish back in 1798. He constructed an incredibly delicate, highly sensitive experimental setup. He essentially suspended a bar with two small lead spheres from a very fine wire. Then he brought two massive lead spheres really close to them. The tiny, almost microscopic gravitational attraction between the big spheres and the little ones actually caused the suspended bar to twist slightly. By measuring the angle of that tiny rotation against the tension of the wire, Cavendish basically did the impossible. He successfully calculated the exact value of big G, and by unlocking that single, missing piece of the universal puzzle, he achieved something that sounds almost like magic. It actually led to the famous historical catchphrase, "Cavendish weighed the Earth." Just think about what a magnificent triumph of human ingenuity that is. We already knew the Earth's radius, right? And we already knew little g, how fast things fall. Once Cavendish pinned down big G by watching lead balls twist on a wire in a small, quiet room, we could plug all of it straight into Newton's equation and literally calculate the mass of our entire world. It is just spectacular. Section 5, Gravity, Altitude, and Depth. Now let's explore a really fascinating quirk of this invisible force. How exactly does gravity change depending on where you are? Like what happens if you go high above the planet or deep inside it? Okay, so this might feel completely counterintuitive at first. If you fly way up high in a plane or a rocket, your distance from the Earth's center increases, so naturally, according to Newton's inverse square law, gravity gets weaker. But what if you dig deep down into a mine? You're getting closer to the center, right? So shouldn't gravity get stronger? Actually, no. As you go down, there is now a shell of Earth's mass above your head, literally pulling you up, which cancels out some of the pull from below. Because there's less mass beneath you pulling you down, gravity decreases in that direction too. So this reveals a perfectly structured mathematical reality. The gravitational pull of the Earth is at its absolute maximum right on the surface. Right where you are sitting or standing at this very moment, you are experiencing the strongest Earth gravity possible. Go up into the sky or down into the crust, and you'll actually weigh slightly less. And that brings us to Section 6, Achieving Escape Speed, Leaving Home. For our grand finale, let's look at the ultimate application of all this math. We know gravity holds us down, but how do we break free? Imagine throwing a stone straight up into the air. It comes back down. Throw it harder, it goes higher, and then it still comes back down. But is there a limit? Can we throw an object with such immense initial speed that it literally defeats the Earth's gravitational field and just never returns? Well, using the principle of conservation of energy, basically balancing kinetic energy against gravitational potential energy, we can actually calculate the exact speed required to pull that off. That magic number is Earth's escape speed, 11.2 kilometers every single second. Let that sink in. Not miles per hour, kilometers per second. If you can accelerate an object to that blistering speed, it will break the invisible tether of the Earth entirely and drift out into the infinite cosmos. And this brilliantly illustrates a vital reason why we are even alive to talk about this today. Compare Earth to the Moon. Earth's escape speed is 11.2 kilometers per second. Gas molecules in our air bounce around incredibly fast, but not that fast, so our strong gravity traps them, giving us this thick, life-giving atmosphere. But the Moon? Its escape speed is only 2.3 kilometers per second. Because it's so much smaller and less massive, fast-moving gas molecules can easily reach that speed and just float away into space. That is precisely why the Moon is a barren, airless rock. Which leaves us with one final, absolutely mind-bending thought. We know the mass of a planet dictates its escape speed. Earth is 11.2 kilometers per second. Jupiter's is much higher. But if you pack enough mass into a small enough space, does that escape speed eventually exceed the speed of light itself? What mysterious dark objects are hiding out there in the deep cosmos where the gravitational pull is so unfathomably strong that absolutely nothing, not even light, can escape? That brings our explainer to a close today. But I hope this journey from falling apples to the very edge of the universe leaves you looking at the invisible forces around you in a whole new way. Keep wondering and keep learning.